So today we're going to start thinking more about fundamental ideas and architectures for reinforcement learning and planning, and how to combine these ideas together. So really, it's there's a lot of conceptual ideas. There'll be much less math in the last couple of lectures, and more just about understanding what it means to do planning, what it means to do learning, what it means to combine these things together. And so rough outline for today, as we'll start off, I'll introduce the area, as usual, a little bit. But then we're going to start to talk about one of the fundamental areas that we haven't explored so far, which is called model-based reinforcement learning. Up to now, pretty much the entire course is focused on model-free reinforcement learning, i.e. where we don't explicitly try to understand and construct a model of the world's dynamics. And in this lecture, we're going to start breaking that apart. We're going to start to talk about, what does it mean to build a model of the environment, and how can we then use that model to plan and perform more effectively in that environment using that model. In the third section, we're going to start to talk about how to pull these ideas together. So we've seen that up until now, model-free based approaches, and then today we're going to look at model-based approaches, but can we get the best of both worlds? Can we combine these together into a single integrated architecture? So we're going to talk about Dyna and other ideas that combine both model-free and model-based methods together. And then finally, we're going to talk about a family of methods that actually are all about planning, simulation-based search, but the main idea there is that we plan by applying reinforcement learning to simulated experience. So this final section is all about architectures where you have some agent, it imagines what's going to happen into the future, and it learns from that imagined experience how to perform better. And we'll see that actually gives us surprisingly effective algorithms for planning within the reinforcement learning context. Okay, that's the sort of map of today. So it's playing with these ideas of learning and planning, understanding what they are, putting them together in interesting ways. Okay, so just to start with an introduction then. So in the last lecture then, we started off by looking at these policy-based methods. We learned a policy directly from experience. We looked at policy gradient methods, policy search methods, where we had some agent, ran its trajectory of experience, the robot wandering through its environment, and at each step it looks at the experience, it looks at the reward it's receiving, and it says, how can I actually adjust my policy so as to do better? In the previous lectures, we looked at learning the value function directly from experience. Again, you see some trajectory of experience, and you use that trajectory to update the value function, and then indirectly use that value function to behave better within the world. So in this lecture, we're going to try something different, which is instead of learning the policy or the value function directly from experience, we're going to learn a model directly from experience. And what we mean by a model is something where the agent starts to understand its environment, starts to understand the dynamics of the environment, how one state transitions to another state, and to understand the reward that environment will bestow for any given action in any given state. So we're going to try and learn that model directly from experience. So we have now our robot wandering around. If it takes a step, it's going to say, okay, well now I know that if I was in this state and I took the action of stepping forward, then I'll end up something like here, and I'll get a reward of whatever reward I observed. We'll use that model now to plan. And what do we mean by planning? Well, just think of something like tree search. Imagine you've got something like a chess playing agent, and it's doing a search tree, and it's trying to look ahead. So what we mean by planning is something like look ahead. We're trying to figure out, by using our model to imagine what might happen going into the future, we're going to use this process of look ahead to construct a value function or a policy. So all of the ideas from the first two lectures can still be applied here. Ultimately, we're still going to be building value functions and policies. We're going to be building them by using this model to perform look ahead, to understand what the environment might do by invoking our model instead of interacting with the real world. And so what we're going to try and do is then integrate these ideas of learning and planning into a single architecture. Okay, I guess the power's not on for some reason, which is why this is blanking. Yeah, good. I just need to wait for that to come back to life. So what we're going to start with is we'll start off by understanding what it means to build a model. A model, again, is something which can be broken down into two pieces. A model is something which tells us all about the transitions, about how one state transitions into another state, but a model also tells us about the reward component of what's happening. So there's always these two parts to a model. So what we mean by a model is perhaps one of the most overloaded terms in machine learning or perhaps even science. or a model can mean many things to many people. For us, in this lecture, it's going to mean something quite specific. It's going to mean something which describes, for any given environment, it's the agent's understanding of that environment, the agent's model of that environment, the agent's understanding of how states transition to other states, and how states lead to rewards. And when we have those things, we should be able to actually plan with them to do look ahead and figure out how to do better in that environment. Just waiting for my laptop to come back to life. It doesn't seem to want to do. Okay. Now we need to wait for the projector to come back to life. And then we need to wait for you guys to come back to life, and we'll all be good. So, let's just try this. Okay, so let's start to come back to our taxonomy that we saw in the very first lecture. Throw your minds way back into the past. We broke down reinforcement learning into two types. We broke it down into model-free reinforcement learning and model-based reinforcement learning. So what do we mean by those things? By model-free reinforcement learning, well, we mean there's no model. What do we mean by that? Well, we mean that the agent doesn't make any effort to explicitly represent the transition dynamics or the reward function that the environment is operating under. And instead, we learn a value function and or a policy directly from experience. So you have some agent, it's wandering through, it applies its favorite algorithm, Monte Carlo learning, TD learning, policy gradients, whatever it is, applies that directly to this stream of experience and comes up with some way to estimate how much reward it can get, or how some way to directly come up with a mapping to which actions to pick in the last lecture. That's model-free reinforcement learning. But today, we're considering model-based reinforcement learning. So that means specifically anything where the agent explicitly represents and learns a model from experience. So now it sees its experience, and it uses that experience to construct an estimate of these transition dynamics and rewards. And it uses that model then to plan a value function and or policy from the model. So what we mean by planning is basically using a model to look ahead, to think, to compute, to figure out what the right value function or the right actions are to select in this environment. We'll see more examples of that as we go through. So if we go back to our original picture that we had for model-free reinforcement learning, it looks something like this. This is the reinforcement learning cycle we had in the first lecture. We've got our agent brain there, thinking about what to do. There's some environment it's in, whether it's the factory floor it's on, or the chessboard, or whatever the situation we've thrown this thing down in. And it gets to take some actions. At every step T, it gets to take an action. And then from the environment, it sees some reward and some state. That was our fundamental cycle of reinforcement learning. So what do we do in model-based reinforcement learning? Well, what we start to do is we replace the real world with the agent's model of the world. So this cartoon version of the world is supposed to represent the fact that we've basically taken away the real interactions that the agent's having, and we've replaced those real interactions with simulated interactions with a model of the environment. So here now we've got, this agent, it's doing exactly the same things, it's taking actions, but now with respect to its internal model, its imagined world. It says, well, hang on, I can think about this. I've got this model of the world. I can imagine what would happen if I stepped forward in this world. How much reward would I get according to my model? What state would I end up in according to my model? And then I can pick another action. I can say, well, if I followed up from there and I took a second action in this world, how much reward would I get? And what state would I end up in? So I can do look ahead, I can roll these things forward, I can build search trees, I can start to think about it, I can start to sample random transitions and figure out what the value function could be, all internally without actually taking any step in the real world. So this gives us the ability to think, to figure stuff out, to look ahead, to plan, and to basically start to understand the best actions to take and improve our policy, improve our value function without any further interactions with the environment. So that's what a model gives us. It gives us the ability to think, to look ahead. Okay, so let's talk about what model-based reinforcement learning is, just try to define it a little further. So model-based reinforcement learning, we can kind of define it by this cycle now, that you could start anywhere on this. I think I would like to start somewhere here, that we have the agent's actual experience. This is it really interacting with the real world, not the cartoon world now. From the interactions with the real world, it's going to build up its model. It's going to learn how that environment acts, how the environment, what the environment does. Every time you take an action in the world, you take some action in the real world, and now you see that actually that led you somewhere. That took you opened the door and you saw some new room. You now change your model to understand what happens when you open the door. Once you've learned a little bit more about your model from your experience, you have a model, and you use that model to plan. This is like your look-ahead process. This is now the slide I just showed with the cartoon version of the world, where you start to have interactions with that model, and the interactions with the model generate a value or a policy, a value function or a policy. And that value function or a policy you then use to act in the real world. So the main idea now is we've interjected, instead of just looping around here, we've added in this model step, where we're using our experience to build a model, and we're using the model to plan and figure out what to do next. And now as a result of that planning, we can make better actions in the world. We can start to really squeeze more out of our model to really start to figure out, to solve our model MDP, if you like. So you can think of this as learning an MDP model, and then here, plan is like solving that MDP, like doing our dynamic programming or figuring out the solution, figuring out the optimal value function or the optimal policy for the MDP that we believe we're in. And then each time you see more experience, you might update your estimate of what MDP you think you're in, so that now when you solve it again, you end up with better actions and do better and better in the real world. So that's model-based reinforcement learning. Really fundamental idea. So it's natural to ask, well, should I do this? What's the advantage or disadvantage of doing this? And I think, perhaps the clearest example would be to take a domain where learning a value function or a policy directly is hard. So imagine you're playing chess, for example. Now, there's a huge variety of different states that you can be in the game of chess. I think there's something like 10 to the 48 or something different states in the game of chess. And if you just move one piece by one square, it can completely change it from being a won position to a lost position. So it has a very sharp value function, which you just move from one of those 10 to the 48 states to another one, and suddenly your value function or your policy completely change. That means it's a hard problem to learn a value function or a policy directly. However, the model is quite straightforward. The model is just like the rules of the game. That, if I move the pawn forward 2 steps, then I will be in a new board position where that pawn has been moved. The model is relatively straightforward. And so if I can use that model to look ahead, I'm able to estimate the value function by planning, by tree search in the case of chess. And that's why tree search is powerful in games, because it gives you the ability to construct a more accurate value function when it might otherwise be hard to estimate that thing through our normal means directly from experience. So really that's perhaps the main advantage is that sometimes a model is a more compact representation than a value function, or not just more compact, a more useful representation of the information about the environment than you might access directly by a value function or a policy. So in addition, it's also possible to efficiently learn a model by supervised learning methods. Like, one thing which is nice about model learning is, like, I was in this state, I took a step, and now I'm in another state. So now by supervised learning, I can say that the input is being in this state, the output is whatever state I ended up in. And it's like there's some teacher saying, look, whenever you started in that state, you ended up in this state. And now you've got a teacher that tells you the right thing. We've got a supervision signal. We can apply supervised learning to figure out the dynamics and the rewards of our model. We can start to learn our MDP by supervised learning. We don't need to wait all the way to the end of our trajectory to figure out where we were after 1 step or 2 steps. And a lot of people talk about model uncertainty as well as one advantage of being model-based. Right? If you want to understand, so sometimes the exploration problem in reinforcement learning is you want to take actions that help you understand the world better. You don't just want to take actions that get the maximum reward from your current view of the world. You also want to figure out if maybe your understanding of the world was wrong. And the model gives you a very useful way to reason about what you know and what you don't know in the world. The model basically tells you all the things you know, and so now you can choose, if you understand your model uncertainty, you can take actions to take you to states where you don't understand the dynamics of your environment very well and choose to go there. Main disadvantage is, well, now we've introduced another moving part to our reinforcement learning algorithm. Like first we're learning a model, and then we're using that model to make a value function. So before, if we were just learning a value function, the only place that our errors could crop in were, we could get errors if we were using value function approximation, then that value function approximator could introduce bias and error into our estimates of the values. Now we've got two places errors can creep in. Like our model might be approximate, and then we're using that approximate model to learn a value function, which might also be approximate. And so there's like two places the errors can creep in, and these things might compound. We're only going to be as good as our model, as we'll see later. If you learn an incorrect model and then plan with it, you will get an incorrect answer. And so what we'll try to do actually later on in this lecture is we'll try to combine the advantages of model-free and model-based reinforcement learning into a single architecture. So what is a model? So I kind of said this informally. Well, let's say the same thing formally now. So one choice for a model is that it's a representation of an MDP. That the world that we're in is some kind of MDP. We might not know exactly what the underlying states and transitions and so forth are of this MDP, but a model means to estimate these things. A model means our view, the agent's view of what the MDP is that it's living in. And so let's say that there's some representation of MDP with some state space, action space, transition probabilities, and reward function. That was our definition of MDP from earlier in the course. And we're going to parameterize this thing. So think of this as now just like, maybe it's a neural network that we're trying to learn with some parameters. And we'll use these parameters eta to represent our model. And we're going to assume that our state space and the action space are known. You can have more complicated versions of model-based reinforcement learning where you also try to learn the state space or the action space. We'll do the simpler case. And so the model now is basically the parts that we don't know that we're trying to estimate. The transition probabilities, like if I'm in some state, what's the probability that I'll move to some next state, and a reward function. And these things are going to just be parameterized by by these parameters eta. And so we've got two things. This is just our usual definition of MDP. We've got something which says, if I was in some state ST and I took some action AT, what's the probability that I'll transition to this next state? And we learn that thing. That's what it means to learn a model. We learn the probabilities that we transition from one state to the next state, the dynamics of the MDP, where the wind will take you next, or where your helicopter will move to if you apply particular controls, and where your robot will move to if you adjust the torques in its motors, and all these things. But we also learn the rewards. And so the reward function is basically just saying, what will the reward be, the expected reward at the next time step, if I'm in some state and take some action. And so both of these are one-step models. You can do longer timescales as well. Here we're talking about one-step models. We're looking at what will happen at time step t plus 1 if I start in time step t. And so you only need one step of experience to learn this thing. You get an example, you can learn this thing, you started in state st, you saw state st plus 1, you can already learn. You don't need to look at successive state transitions after that. Okay. And for this particular definition, we typically assume these things are just independent. We can learn them separately. It's easy to change that. Yeah, question?
I think I don't quite understand the chess example and what you gain from using the model-based view of things. So when you're doing model-based learning, the dynamics are still, they're sort of fixed. There's no like probability distribution. There's only one. If you make an action, then you deterministically transition from state to state. So you still have to learn the reward function. And is that not just the same thing as doing it like in a purely value-based way?
No. So good question. So the question is, isn't it the same to learn a reward function as to learn a value function? And the answer is no. Like in chess, what would it mean to learn the reward function? Well, the reward function in chess might be something like 0 for losing a game and 1 for winning a game. And now all you need to learn is that if you're in a checkmate position, that you lose, and if you've checkmated your opponent, then you win, and if it's a stalemate, then it's a draw, 0.5 reward. You don't need to, whereas if you're learning a value function, you need to learn about all the states where it's not a terminal position. You also need to learn, if I'm in some complicated position with all these pieces distributed around the board, and and there's still a lot to play for in that position, the reward learning problem is easy because the reward will always be 0. in that situation. The reward function is just 0, 0, 0, 0, 0 until the end of the game, and you either win or lose. So that's an easy learning problem. You're just learning that the reward is 0 unless you're in a checkmate position. So that learning problem is much easier. You're just learning to classify positions as checkmate or not checkmate. And that's just about learning, does the king have any moves left? Whereas actually learning to understand, am I likely to win from this position? Like, I'm in some early middle game position or something. What's the probability that white will win from this position? That's a complicated learning problem. Now you need to figure out, well, actually from this position, maybe there's a 72% chance that white will win from here. It's a complicated thing. And so the main point I'm trying to make is that there are situations where it's really an argument that planning sometimes helps. Like, but being able to plan sometimes helps, because trying to learn the value function directly, there are at least some cases, like these very tactical games like chess or Go or whatever, where it's necessary to plan to figure out exactly what situation you're in. That without doing this process of look ahead, it's very hard to say who's ahead or who's behind in the position.
Okay, and so like being able to look ahead and plan is not like a valid move to make when you don't have
So planning necessarily means that you've got some way to roll forward your state to say what would happen if I was in some. So if we take chess as an example, what's the model in chess? It's basically the rules of the game. Okay, it's the thing which says I'm in this position. How do and I take an action. What position will I be in next? So it's just the rules of the game. That if I take this move, certain moves might remove pieces from the board, or they might just change where things are. And so we're just trying to understand the rules of the game then. And if you don't tell anyone what the rules of the game are, then that would be model-based reinforcement learning. You kind of have to figure the rules out and then use those rules to plan with. Or we could just consider the planning problem without the whole reinforcement learning problem, which would be someone tells us the rules, someone tells us the MDP, and now we need to plan with it to figure out what move to play. So those are both interesting problems, but the chess example is just to illustrate the case that there are some situations, there are some MDPs where it's very hard to do well in that MDP without planning. So there is a case for being model-based. Okay, so we're going to take this idea of trying to learn an MDP. We've got our transition dynamics and our reward dynamics, and in general, so chess here it isn't maybe the best example for this, because chess is deterministic. Here we're trying to understand, well, what happens in stochastic situations where you've got a helicopter and the wind might blow it one way or the other. We want to learn that as well. And so the goal really is to estimate this model from experience. So we've got our model, our MDP, parameterized MDP, maybe our neural network representing what's going to happen next, or our linear function approximation, or whatever it is. And we just see our experience, our usual stream of experience, states, actions, rewards, until the end of the trajectory. And but now it should be relatively clear that we can actually just transform this one into a supervised learning problem. So specifically, I was in state S1, I took action A1, and I ended up seeing an immediate reward, that was the reward we got from that time step, call that R2, and the state that we ended up in, S2. So that's just after one immediate step. We see what reward we got, we see where we ended up, and that becomes an example that we can learn from. And then we've got another example, which is then I was in state S2, I took action A2, I ended up getting some immediate reward, and ended up in some new state. That's another example. We collect together all the examples that we see from all of our trajectories. That gives us our training set. And we can use that training set to basically do regression to learn the rewards. So we're trying to now split this into two parts. We're going to split it into the reward part and the state transition part. You don't have to split it, but it can be useful. One reason it's useful is that these are kind of different types of supervised learning problems. So to learn the reward function, we're just trying to learn what's the how much reward will I get in expectation from taking some state S and some action A. If in S I take action A, how much reward do I expect to get? That's a regression problem. We're giving an input to our regression problem of state and action pair. We're trying to estimate how much reward we'll get. And we're just going to use all of these as examples to train this regression problem up. But we've also got a density estimation problem. We're trying to learn something stochastic, which is if I'm in this state action pair S comma A, if it's a stochastic environment, I might say, well, I want to learn the whole distribution over what next state I'll be in. That maybe there's a 30% probability the wind will blow me left, 70% probability the wind will blow me right, and I want to estimate this whole density. And so we can transform the model learning problem into two types of supervised learning, and then pick appropriate loss functions for these things. So if you're doing regression, you might choose to optimize for mean squared error. If you're doing density estimation, you might choose to optimize for KL divergence, like make your distribution as close as possible to the empirical samples you store. And I'm not really going to go into the details of how to do this, except for one simple case. And really the idea is just to find the parameters that minimize our empirical loss. So we see all of these examples, and we want our loss to be as small as possible across these examples that we've seen so far. So that's how to do model learning in a nutshell. And you can kind of apply, so everything that you've ever seen in supervised learning can be applied here. And really that's all I'm going to say about it, except for this question.
In this situation we're considering here, do we know our state space, or are we actually able to, say, make our own features?
So for the purpose of these slides, we're assuming that we know the state space and the action space. In general, yes, of course, we want to learn our own features, and that's typically a very good idea, and it may well not be the case that the raw inputs that we're given are useful for learning the transition dynamics, and you might well want to figure out a better representation of the state space that helps you understand how the MDP is rolled forward. So you can also choose to learn the state space or indeed the action space, but that's a more complicated version. So let's just make this concrete by thinking about examples. So I will talk about the simplest possible case in the coming slides, which is the table lookup model, where basically for every state action pair we estimate the reward and the next state separately. In general, of course, this doesn't scale, and it's usually a bad idea. So you can pick your favorite approach. You could make a linear model where you basically say, what's the expected next state if I have some features describing my state in action, what will my expected next features be? So we can basically apply a linear model to our feature vector and say, I start off in some features, I'm this far from this landmark, this far from this landmark, and now I'm going to make a model that says, if I go forward, then I'll be a little bit further away from this landmark and a little bit closer to that landmark. A model that sort of in expectation tells us what will happen by making, say, a linear map from features to features. We could have a Gaussian model to, rather than just making an expectation model, we could model the whole distribution of next states using, say, a Gaussian. You can take that further and have a Gaussian process, a non-parametric model. You can have a deep belief network to, pick your favorite supervised learning method and your favorite representation, and you will be able to apply it here. ... means a lot of possible things. Okay, let's consider the simplest case, the table lookup model. So what's a model now? A model is sort of an explicit representation of the MDP. And so if we want to basically understand from this state, if I consider some specific state I was in, and I want to know, well, I'm going to keep a separate representation for this state of where I will go next if I start in this state and take a particular action. All I need to do is count. I just count how many times from here I count, and maybe I ended up over here 10 times, and I ended up over here 5 times. And so now I just count those things and use the empirical counts to give me a probability distribution over where I'll go to next. So this is just saying the same thing in maths, saying that our transition dynamics are going to be the average of this indicator function, which tells us every time I ended up in this particular S prime, in this particular state S prime. We're just counting the times I ended up in that particular state. And the reward function is basically just taking an average. All the times I started in this particular state in action, let's take the average reward, the mean reward of all of the rewards that I got from that point onwards. So this is just the intuitive thing. Don't even need to look at these equations if they're confusing. It's just using indicator functions to say, let's do the obvious thing, which is to count the transitions and assign my probabilities proportional to those counts of where I ended up next, and to take the mean of the rewards that I've seen so far and to use that as the reward function. So, is that clear, first of all? Good. But there is an alternative way to set up the same model, and the alternative is to basically just remember things. So you can just record the experience that you've seen so far. So you can just record that when I was in state ST and took action AT, I observed reward T plus R T plus 1, and I observed that I ended up in state ST plus 1. And now if you want to actually sample from this model, all you need to do is take the set of tuples that are consistent with the state and action that you want to know about and sample it uniformly at random from those. And then you sample, well, one of these rewards was that, or one of these next states was that, and you can just sample from those tuples. It's equivalent. Here we're going to talk, so it's basically a parametric and non-parametric approaches. So those are examples of the two families of functional approximation for the model learning. But they basically give you the same information. Okay, let's make this concrete. So we've had this example once before, but I'm going to take it just one step further in this class now. So we had this really simple A-B example when we were talking about understanding temporal difference learning. So we're going to use it for a different purpose here, which is we're going to do model learning. So just to remind you of this problem, we've basically got two states with no discounting, and we just see these episodes of experience from state A and state B. So this means on the first episode, I started in state A, got reward 0, then went to state B, got reward of 0, and then the episode terminated. Second episode, I started in state B, saw a reward of 1. Next episode, started in B, reward 1. Until finally, started in B, got reward 0. So we can take this experience, and as we did before, we can build a model from this experience. This is what we saw in the TD, what TD was kind of doing implicitly. Now we're making that explicit. We're explicitly building this model. So we're going to build the model, the table lookup model, that corresponds to these counts and these rewards that we've seen. And so all we need to do is to count and say, well, every time I was in A, I transitioned to B. So if I count those things, I can make this transition here to say 100% of the time I transition from A to B. And I can count that from B, on 6 out of 8 of my occasions, I transition to the terminal state with a reward of 1. And on 2 out of 8 occasions, I transition to the terminal state with a reward of 0. That gives me these two arcs here. So it's just counting. That's all that's required to make a table lookup model. So now we've got a table lookup model. Let's use it. Let's start to understand how to use this thing. So the next step is, and this is the important step, is to plan with the model. So far we've just talked about learning a model. What does it mean to plan with the model? So now we've got our MDP that we've learned. We've estimated our MDP, for example, the one on the previous slide. And so now planning basically means kind of solving that MDP. It means using that model that we've got to try and find the best thing to do. And so we're going to solve that MDP to find the optimal value function and the optimal policy, and hence pick the best action. And so you can use your favorite planning algorithm to do that. And we've seen a bunch already. We've seen in earlier lectures dynamic programming methods like value iteration and policy iteration. So these methods, when we talked about them before, we thought, okay, well, you can't use these to do reinforcement learning because you have to be told what the MDP was to apply them. But in this lecture, we're saying, well, actually, you can do reinforcement learning with those. All you need to do is learn your model, first learn your model, and now you have the model in your hands, so you can use that model to apply dynamic programming. Or you could use that model to do something like tree search, or a variety of other planning methods we'll start to talk about later. So, again, let's make that concrete. And the method I'm going to talk most about in this lecture is what we call sample-based planning, which in some sense is the simplest possible way to plan, but it also turns out to be perhaps the most powerful way to plan. And certainly the empirical results support that, at least in complicated domains. And the idea is to only use the model to generate samples. So unlike dynamic programming, where you actually look at the probabilities of transitions and kind of integrate over those probabilities, we're just going to use the model to generate samples. We're going to treat our model as if it's the real environment, and we're just going to interact with that environment and see samples of where I end up. So instead of knowing that 75% of the time the wind will blow me right and 25% of the time the wind will blow me left, I'm just going to randomly sample something from the environment. I'm going to be like, oh, look, I got blown right on this occasion, and I'm going to learn from that sample, just like we do when we interact with the real world. So we sample a next state. If we're in some state S, A, I'm going to sample the next state, and I'm going to sample the reward from the model. And then I'm just going to apply our familiar model-free reinforcement learning to those samples. We know how to learn from sample trajectories. We know how to learn from samples where I've just randomly seen what happens if I interact with my environment and the wind blows me around, and I take this whole sequence of actions and I end up over here and I get some sequence of rewards. That's the problem we've been studying all along, which is model-free reinforcement learning. So the main idea here of sample-based planning is to just use the model to generate samples and then to apply model-free reinforcement learning to these samples. Another way to think of that is that the agent has some model in its head, it imagines what is going to happen next, and it plans by solving for its imagined world. It simulates experience. I'm imagining, so instead of actually walking ahead, I'm going to imagine, what will happen if I put my foot there, and then my other foot there, and then my other foot there. I can imagine all the rewards, imagine I might fall over, imagine I might, get to my pot of gold at the end of this thing. All the things that might happen, I imagine those, solve for my imagined experience by just applying reinforcement learning to those sample trajectories, to those imagined experiences. And it turns out that not only that we've given something up, which is we've given up these probabilities, but that actually sometimes gains us something. It often gains us something. And it gains us efficiency because we don't have to consider that it breaks the curse of dimensionality. That even if we knew the model, even if we have the model in our hands, it's often a good idea to sample from that model, because by sampling from it, we focus on the things that are more likely to happen, rather than doing like these naive full-width look ahead where we consider all events that might happen, even if they're low probability. So sample-based planning methods are often much more efficient. We'll see examples of that. So let's go back to our AB example. So what would it look like here? So we started off with this real experience. We generated a model. And now we've got this model. We can use this model to sample experience. So we've got this model. So let's imagine now that we could sample what happens. We could sample some trajectories from this. The model should also include some model of where you start in this case. So let's say, we sample our first trajectory and say, okay, the model says I'm going to start here, and we roll the dice, and the dice says, okay, we should follow this 75% here, and we end up with a trajectory that says B1. And we sample again, we find that we start in B, this time we end up in B0. We sample again, we get B1. We sample again, we end up starting here, we get A0, B1. And B1, and A0, B1, B1, B0. So we're just sampling from our own model. And it should be clear that the advantage of this approach is that even though we've only seen this number of real trajectories, that we're able to sample as many trajectories as we can given our computational budget. So we can sample, if you've got a real robot, it's quite slow and painful to work with a real robot, but if it builds a model and imagines what might happen, it might be able to sample millions of trajectories of hypothetical experience, even though it might only have seen one or two trajectories of real experience. So that's the advantage of building a model. Once we have that model, we essentially have infinite data. Or the ability to generate infinite data. So now, let's take the final step. So the final step is to say we started with our real experience, we've built a model, we've sampled experience. Now let's do the final step, which is to learn from our sampled experience and apply, say, Monte Carlo learning to these trajectories. That's the canonical model-free reinforcement learning algorithm. If we did that, we would find that the value of A, or what's the value of A over here, well, I started off in A here, I ran a trajectory and I got a return of 1. Started off in A here, ran a trajectory, I got a return of 1. So from this set of samples, we would estimate that the value of A is 1, and the value of B would be, I've got 6 trajectories where B led to a reward of 1, and 2 trajectories where I got 0. So we would say the value of B is 6/8 or 3/4. So we started with real experience, we generated a model, we sampled experience from that model, we solved by model-free reinforcement learning to give us a value function, and that value function is different to the value function we'd have got if we'd applied it to the real experience directly, but asymptotically, if we run more and more and more, our model will get more and more accurate, we generate more and more data from our model, we will ultimately end up with the right answer again. So it's a different way to arrive at a solution to the model to a particular MVP. Is that clear? No? Good.
Did you, this sample experience, you based it, so when you say I start from B and I got 1, does that mean that's based on your previous experience there, the real experience?
So we just used the real experience to learn this model here. And we also, the missing part, which is maybe what's confusing people, is the model also needs to include an initial start state, like some probability of do I start in A or B. So let's say that we have that probability as well.
That's not my problem.
Okay.
The problem is here for 1, 2, 3, 6 times from B you get 1, and then 1B gets 0.
2. From this B you got 0, and from this B you got 0.
Alright, but isn't that the difference? Because you start from A, you still have that. Okay.
Remember how we learn a model. We learn a model by one-step supervised learning.
Alright.
At every state, we look at where we started. So if I start here, I start in A, and after one step, I get a reward of 0. That's my reward, the example for my reward model. And after one step, I end up in B. So those are the transitions we're learning from. We're learning from one-step transitions. We're learning to build a model. So now that says we just look at all the one-step transitions from A, and if we average over those, that's just this one here. We've only got one example of that. So now we have to say that this transition should give us a reward of 0. Or we don't have to. This is the maximum likelihood model. And then learning from this example, that is the model that we would do by the table lookup procedure that I outlined in the previous slides. Okay. And similarly for B, we just look at the one-step model. I started in B, I got the reward of 0, episode terminated.
Okay.
So for all those. Okay, question.
But how do we change the number of episodes that we need to look at? Because if we build a model that, we might build a model based on a lot of the sample experience, but maybe our model doesn't not correspond to reality at the end.
Right.
So we need some sort of feedback as well.
So the question's a good one, which is how do we trade off learning about how much time we spend generating the model compared to how much time we spend computing with the model to sample experience, which is a good question. And the answer, I think, the right answer would be that typically with real experience is often at a premium. So you kind of want to use all of your real experience, and your robot is always generating as much real experience as it can. You use all of your real experience to generate the best model you can, and now you've got some, think of it as an anytime procedure. Like you just keep in as much time as you have until you make your next decision. You keep simulating experience, generating more samples, updating your estimate of the value function, updating your estimate of the policy, and at the time when you have to make your next step, you just look up the best action from your policy or from the value function at that point. So these things are, think of it that planning is always going on. You plan as much as you can, and planning is always going on. And acting is also always going on. You act at whatever rate you have to act in the real world. You plan at whatever rate you can think at. And these things just happen at their natural rates. That's one way to understand it. Okay, there's a lot of questions here. Good. I think there was a question earlier from...
Yeah. I'm wondering about uncertainty in the model.
Yeah.
So in some states of the experience, we experience them much more often than others.
Yes.
So our estimates of what might happen from them are much more precise than in others.
Okay.
Does this influence our action that we take?
So it was a great question. The question is, what happens if we want to take account of the uncertainty in the model? So there's going to be some bonus slides, which we won't get to today, on Bayesian model-based reinforcement learning, which basically says, here we just made a maximum likelihood model. But what happens if you want to, take account of uncertainty and say, well, maybe the model looks like this, but really we shouldn't be completely confident of this transition being 100% from A to B, because we've only seen one transition. So maybe we've got some prior that it should have been something else, and we can combine our prior expectations with our data. And so Bayesian model-based reinforcement learning lets you do that at some computational cost. And so I'm just presenting the simpler case here. Okay, I'm going to take one more question and then move on. So I think, yeah.
That's just a simple one. How do we get rid of A is equal to 1? Because we get 0 from A, right?
No, we're looking at the return, remember, with Monte Carlo learning. Okay. So you start here. The whole return is what we're averaging over. The whole return is 0 plus 1, if we're assuming this is undiscounted. Okay, last question. And then. Okay, good. Okay. Right. I'm going to move on, if that's okay. Just I want to move on. So what happens if our model is not right? What happens if we have an inaccurate model? What happens if we haven't seen enough data to really understand the true dynamics of the world, or the true reward function of the world? So we should understand that we will never, when we plan with this imperfect model, we shouldn't expect to get the right answer. But the performance of model-based reinforcement learning is only as good as the optimal policy for the model that we've learned. So we learn this approximate MDP with our parameterized transition dynamics and reward function, and now we want to know what's the performance that we can achieve in this world. Well, if we were able to just do a perfect job of the planning side, if our planning was optimal, we would solve this MDP. But the solution to this MDP might not be the right way to act in the real world, because the real world was different to our model. And so we can only do as well as the performance of our approximate as the solution to our approximate MDP in the real world. So model-based RL is only as good as the model that we've learned. And so we should be okay with that, though, because ultimately we're always going to be approximate when you haven't seen enough data, and it's just a different way to be approximate. And the way that we're being approximate in this case is by learning a model first and solving to that model, as opposed to approximating something else like the policy or the value function directly. Sometimes it's going to be better this way, sometimes it's going to be worse this way. It's a different route through the reinforcement learning problem. So some things you could do would be to use model-free reinforcement learning when your model is wrong. Like if we know that our model is just junk, don't trust it, trust your value function or your policy instead. Another solution would be, as suggested, you could reason explicitly about model uncertainty. This is the Bayesian approach, for example. You can understand that you're in a situation where you don't know about your model in one state. Okay. So, are we okay so far? This is the sort of core ideas, model-based reinforcement learning. So, any last questions? Yeah.
And is the extended to continuous state and actions?
Yeah, absolutely. So this can be extended to continuous state and actions. Exactly everything I've said so far applies, except that you can't apply table lookup methods. You need to have some way to generalize across states and actions, because you'll never revisit exactly the same state and take exactly the same action again, because it's continuous. And so all of these model learning approaches, the normal case is that there's function approximation. You've got, say, some neural network representing your transition model or whatever it is. Yeah.
Could you give an example of the problem where it's better to sample from the estimated model, just then directly using expectation?
Okay, so I already tried to give examples of that using the chess example. So I spent a little bit of time on that. So if it's okay, I think I'll move on. Yeah, I think again, let's think of games where there's a lot of MDPs, where there's a lot of kind of sharpness to the value function, a lot of tactical decision making that needs to be made that's very precise and depends very sharply on exactly the configuration. Could be some maze that's very different each time. So you take a maze, you randomly generate the maze so it's different every single episode. And now, if you try to learn a value function directly, it's like you have to just look at your maze and figure out, well, what's the way out of this maze? That's a hard thing to do. Whereas to learn a model for that maze is trivial. It's like, if I move north, I'll end up one square to the north in this maze. Or if I move east, I'll move one square to the east unless there's a barrier there. Okay. Right. So next section of this, we're really going to try to bring together now the best of model-free and model-based reinforcement learning. Try and construct something which has the advantages of both, pulls them together. So we're going to talk about these integrated architectures that combine the two elements together. And what we're going to do is we're going to consider like two sources of experience. We've basically seen two ways to generate experience now. We've seen real experience that's sampled from the environment, sampled from the true MDP. So this is what happens when our robot's really interacting with the world. This is the real world. The real world is that you're in some state, you take some action, you see some next state. And now you're in some state, you take some action, you see some real reward. These are our samples that we're generating, our state, action, reward, next state. Real interactions with the environment. But now we've seen that we can also generate experience in a different way. We can use our approximate learned model, take our approximate MDP, and sample from that. We can sample states from our own model. We can sample rewards from our own model. We can generate states, actions, rewards, next states. We can generate this experience, these streams of experience, just by imagining what would happen next. By rolling forward our imagined model. I was in this state, I query my model to say where will I end up with next. I query it again to say where will I end up in next. Query it again. I end up with some whole stream of experience that I'm generating by interacting with my model. So we've got two sources of experience, real and simulated. Yeah, good.
seems to me that everything you've experienced so far, it's just going to teach you to exploit what you've seen, and it's not going to teach you the benefit of exploration.
Okay, so good question. How does this relate to exploration? Can we learn how to explore? So we, in some sense, exploration and exploitation, which there's a whole lecture on next week, is sort of orthogonal to this, in that, you know, this doesn't tell you anything about, we're not saying you have to follow the optimal action according to what your approximate MDP is saying. There's nothing that says we have to just act greedily with respect to that. We can also choose to explore. But you're right that you sometimes also need to explore, and it's good to understand that you don't always want to act greedily with respect to your value function. And the value function in this case is arrived at by solving for your model, and your model isn't perfect, so we still need to explore to make sure that we start to understand the parts of the world we don't know at the moment. Okay, so we're going to talk about how to integrate learning and planning together. So the first slide of the introduction, we basically started off with this taxonomy again. Model-free RL, there's no model, and we learn the value function or policy from real experience. Model-based RL, where now we're considering sample-based planning, as an example, where we learn a model from real experience, and we plan by simulating experience from that model by interacting with that stream of imagined experience and learning from that stream of imagined experience. So what if we combine these together? We end up with something known as the Diner architecture. This is a old but fundamental architecture by Rich Sutton from several years ago, where you learn a model from real experience, but then you also, so you learn the model from real experience, and then you use both sources of experience. You use both the real experience and the simulated experience to learn your value function or policy. So we basically use all our sources of experience. Sometimes we should trust the real experience, sometimes we should trust the simulated experience. The Diner idea says, let's just use everything. Let's integrate everything together. Let's use all the experience we've got and combine that experience together to give us a value function and a policy. So it looks a little bit like this, where we've basically taken our model-based reinforcement learning loop, where we went from experience, learned a model, plan with that model to give us a value function, act with that model in the real world to generate more experience. And the thing which we've added in is this arc here, where we've now said that in addition, we don't just learn our value function by planning with the model, we also learn our value functions directly from the real experience in the real world. So we learn the value function or policy in two ways. From real experience, just like our usual TD learning or Monte Carlo learning from earlier lectures, and also by sampling from our model, running imagined trajectories, and learning the value function or policy from those imagined trajectories. We've got those two sources of experience coming together. Let's exploit them both. Let's get the most out of this by using both of them. Question?
If we have something like chess, where you have to make such kind of very long strategic decisions, wouldn't somehow using direct RL when you're estimating the value function on the experience, that let's say that's going to give you something like the average work given the move, wouldn't that somehow make the algorithm who does the tree search based thing a bit worse when adding that part?
So it's a great question. So the question is, does this arc sometimes make things worse? I've argued that there are cases where you should really trust this guy more than this guy, and so can it be the case that this makes things worse? Possibly, except that I haven't said anything about how you combine them together. So if you combine them together in a smart way, then you can basically make sure that you always make things better, because you can understand how well you're doing with this one, and you can understand how well you're doing with this one, and you can combine them in a way that understands that you should take more account of the more accurate estimates of value. So the canonical Diner algorithm looks something like this. So this is the Diner Q algorithm. It's the simplest version of Diner. And all it says is, let's just start off with some action value function Q and some model. And all we're going to do is basically use this very, very simple kind of model we've looked at. And table lookup model. And we're going to plan with our table lookup model in addition to the real experience. So basically what it means is, every real step in the world, we take a real action in the world, we see where we ended up, and we do two things. We do our usual, say, Q-learning update here, SASA update, where we update our action value function a little bit towards our one-step look ahead of what happened after one step, our TD target after one step. So this is Q learning here. We just update towards what we thought was the best Q value after one step. But we also update our model. So we update our model by supervised learning a little bit towards the reward that we observed and the state that we observed after that one step. So this is just updating our model in some way. For example, updating our table lookup model. And then in addition to this real step of learning, we have this inner loop. This is the thinking loop. This is the learning from imagination loop. This was our model 3 part. But now we can just imagine things, or we just sample n different samples from our model. So what we can do is we can just start with some random state that we've already seen, sample some action that we've taken, and just sample this from our memory-based model. And now what we do is we basically imagine that transition. We say, okay, well, now let's, according to my model, if I started in this state and took this action, I would get this reward and end up in this state. So let's imagine that transition, and let's apply a Q-learning step to that imagined transition. So if I imagine now that I would end up in this new state S prime, then let's actually just now apply a Q-learning update to that to say, and update our Q values from where I started towards the reward plus the best Q value from where I ended up in my imagination. And if we keep sampling and applying this idea, then we can do better and better by just sampling different parts of everything we've seen, sampling our model and improving it. That's the diner idea. It's the simplest version with a very simple model. So what does it look like? So you can basically take some kind of simple maze environment like this, and so we're starting in this state here, we're trying to get to this goal here, there's some grid world, you can go northeast, southwest, you know, usual deal, there's the reward of -1 per time step, you terminate when you get to the goal, that's our standard grid world. And now, let's consider what happens if we use diner. And what we're going to consider is different amounts of thinking time. In other words, we're going to consider different values of n here, like how much thinking do I do, how much do I loop over these samples from our model, how much simulated experience do I generate in addition to the real experience. And what we see is that if I don't do any planning, like if n is 0, if I don't use any imagined experience, this is our standard model-free reinforcement learning approach down here. We get these kind of noisy samples, and after say, I think this is the number of episodes down here, and after say 30 episodes, we've figured it out. But if we start to plan, if we start to do just say like 5 imagined steps for every real step we take, we see that we're much more efficient. We're much more data efficient. After just a couple of episodes, we've already figured out exactly how to get to the goal. We're sort of almost at the optimal solution already, which is down around 14 here. So we squeeze more out of the data we see by first building a model and then using that model to plan. And then it's like we're imagining we might have seen some random kind of walk around here in our first episode, but that random walk was enough to tell us that from here I can transition to here, and from here I can transition to here. And when you put all those pieces together, you've got enough in your model to really, now when you keep sampling your model, you can basically sample many more trajectories now and figure out from those samples exactly the right way to move around this maze and get from S to G. Yeah, question?
So as you've shown on the graph, would it be the case that in step 1 on the x-axis, these would all start in the same place?
You mean do they all start from S?
No, I mean on this graph, the
I
graph
see.
x-axis starts from
Do they all start with the same initial conditions?
So they all start with the same steps per episode?
I think they would all...
They all perform the same?
So, I mean, there's some randomness here, so you can't guarantee that any experiment would be reproduced precisely. Even if you reran the same experiment, you might get different values. But the distribution of scores that you would see would be the same, like the starting point would be the same for all of these algorithms. So yes, it's not shown here, but they basically all start doing some really stupid first episode.
Yeah.
Because there's not much. Actually, even that's not true. Even within one episode, Diner can do better.
Okay.
Not necessarily in this example.
Right.
So imagine that we change the problem slightly, and we make it the case that these are bad states that you could kind of randomly go into and that really hurt you. Okay, but they don't. So whereas the original problem, you can't even walk into these.
Okay.
If we consider that problem, now you would start off occasionally wander into these states, hurt yourself, but you build up a model that if you're in this state and go right, you'd start to understand that hurts you.
Yeah.
And now if you use Dyna, you would plan more efficiently to understand how to avoid getting into these situations where you end up on these states.
Yes.
So let's change it even more and say there's a little bit of wind in this environment as well. And with Dyna then, you'd learn quite quickly to avoid being close to these states, because you would learn just from your random stumbling around, you would learn that you shouldn't be somewhere that's close to this because you might get blown into it. You start to imagine all of those transitions that took you into that, and you learn from those imagined transitions. Whereas using direct model-free reinforcement learning, you have to experience these transitions an awful lot to figure out how to back up your values all the way through, and you just need more data. So even within the first episode, even before your first episode is terminated, you could do better. In this particular example, there's basically no signal until you get to the goal, so I don't think there'd be much difference between them. Cool. Right. This slide is just to show that we can change the environment. So we can start off in this environment. We can basically start off. So again, we've got a grid world. We're trying to get from here to here. There's a barrier here. And so now let's see what happens if partway through we were actually to change the environment. We were to change it, so we would move the passageway from here to here. And let's think about what effect that's going to have on the dynamics of our learning algorithm. So what's going to happen? So we start off, think eventually after some amount of learning, we stumble around for a while. We start to sample transitions using our Dyna algorithm. We figure out this optimal policy here, and then all of a sudden things change, and we discover we're in this new situation. What will happen? Well, we'll start off trying to stumble through here, and our model really thinks that this is the way through, so we'll spend quite a lot of effort getting through there, but we need to make sure that we also can now discover this new state here. So again, this is where the exploration comes in that someone asked about earlier, that we need to make sure that we continue to explore, so you can slightly modify the algorithm to have a bonus to make sure that you basically have a bonus for states that you haven't visited very much. That's this Q+ idea, and that encourages you to kind of explore around and very quickly find this changed state so that you can find your way through and solve the problem more efficiently. But the main point is that after a while, when things change, you basically end up flatlining for a while. You flatline because your model is telling you to just keep going over here. You're planning and you really believe that this is the way through, and even once you exclude that, you then have to kind of try other things again and figure out that there's something better. Yeah?
On the left-hand side of the graph, why did DynaQ+ rise more quickly?
Because it explores more effectively. Because DynaQ+ has a bonus that helps you identify new parts of your state space and learn about your model more effectively. So instead of just stumbling around until it discovers this way through, it's got a bonus that encourages it to believe that states are better that it's never experienced transitions from. So it's kind of encouraged to go to new places and get this bonus there. And we can also do the converse, just one second. We can do the converse where we can make the problem easier instead by making another, by starting off with this solution and then suddenly adding in an easier solution here. But we notice that this one is easier for the algorithms to deal with because our model, assuming we've already explored this, it just needs to see, so it will already know about this thing, so it will continue getting that score. If you don't explore anymore, it will continue using this pathway through here. That's what these lines are here. But if you tell it to explore a little bit and encourage it again to keep revisiting states that it hasn't visited for a while, it will discover that things have changed and then it will get taken to a new part of the state space. Okay, one question, then I'll move on.
I just wanted to know what is the Q and Q+ difference.
It's basically whether there's a bonus for states that you haven't visited. That's it. It gives a bonus to encourage you to explore more. Thank you. Okay. So, are we all good so far? I think people are tracking. The last section is really a different view on planning now. So what we're going to do is we're going to spend a bit of time. So we've talked a lot about model-based reinforcement learning. In this last section, we're going to back off to just one part of that, to the planning problem. You could still imagine we're doing model-based RL where we're learning a model, but we're going to focus more on the planning part, how to plan effectively. And we're going to consider this idea of simulation-based search, where we're really going to explore this idea of taking samples from imagined experience, sampling our model to generate trajectories of imagined experience. And we're going to push that further, and we're going to see how it can be used to make state-of-the-art search and planning methods. So the key ideas that we're going to use are sampling and forward search. So first of all, let's understand what those are. So forward search algorithms don't explore the entire state space. It's not like, so far with Dyna, we were basically saying, well, let's randomly sample transitions from our entire state space, everything we've seen so far. Here, we're saying, well, actually, there's one state we care a lot more about getting the right answer for, and that's the state I'm in right now. Now has this kind of special importance. If I'm on a mountain and I'm climbing up that mountain, what I really care about is, what's the next step I should take on that mountain to get to the top or to get back down it. I really don't care about, what I should eat for lunch when I'm back home the next day. That's kind of irrelevant to me actually surviving in that situation. So the current state is particularly important. We need to make sure that we get the right action from that current state. And the way that we can do that is by forward search, by focusing on what's likely to happen next in the short-term future. And so one way to do that is by look ahead. You start at the state you care about. This is now, our state ST now. And we're going to build a search tree with this current state, this ST, this is our root state, this is our now, our moment that we're in, at the root. And we start to do look ahead, where you could do this exhaustively. You could say, let's start in this state and build a search tree that says I could take this action, I could take this action. The wind might blow me to here or to here, and then I could take this action or this action. That might terminate the episode. This might blow me to here. Take this action here, and so forth. You can build the whole search tree. You can look ahead. You can use your model to tell you what will happen next for each of these. And the model tells you, if I take this action, I could get blown here, or I could get blown here. We have the model. And that lets us look ahead. It lets us look at this whole tree of contingencies of what might happen in the short-term future. And the main point of this slide is to say that we don't need to solve the whole MDP. Solving the whole MDP is a big waste of resource. We just need to focus on the sub-MDP that starts from now. What happens in some unreachable part of the state space or something we're not going to reach for another year from now doesn't really matter to us. It just matters the sub-MDP that we're in right now. Let's do well for that. And sometimes that can be dramatically easier than solving for the whole MDP. That's forward search. We solve for the sub-MDP starting from now using look ahead. So simulation-based search is a forward search paradigm that uses sample-based planning. In other words, what we do is we start from now and we imagine what might happen next. We imagine a trajectory of experience by sampling it from our model. So we literally say, right now I am in this situation. I'm in this position in my game of chess, and I'm going to imagine what my opponent might do and what I would do after that, and then what the opponent might do after that. I imagine the whole sequence, or I'm climbing up the mountain, and I imagine if I was to put my hand to here, I'd be in that state, and then I'd have to move my hand to here, and then my foot to here. I imagine the whole trajectory out, and then I learn from that imagined experience. But it's forward search because we're always starting from now. We're not starting from some arbitrary part of the state space. We always root it from the current moment and imagine forwards by rolling into the future. And that gives us a real focus on what will happen next, rather than distributing our efforts over irrelevant things. And the sampling helps to focus us on what really matters, because we sample actions that we choose, and we sample things which are actually have high probability from the environment, because that's what sampling does. So we end up seeing the situations that really matter. We focus in on the important parts of the space very quickly. And then what we do is, once we've got these trajectories of experience, we apply model-free reinforcement learning. We treat this just like usual. We say, okay, I'm starting here, I'm running some trajectory, I start from here again, I run some other trajectory, start again, run some other trajectory. That becomes the source of experience, and we apply our familiar model-free reinforcement learning algorithms to those trajectories. And that is simulation-based search. So, what does it look like? So we start from now. We start from this ST. This superscript just means, you know, which simulation we're in. We run from 1 to big K of those simulations. And we generate multiple episodes of experience. Start from our root state, action, reward, state, action, reward, all the way to the end. We do that big K times, and we sample these things from our model, or from the real world if someone gives us the real end. If someone tells us the rules of chess, we don't need to learn it. And now, we apply model-free reinforcement learning to this data, to our simulated experience, and we use our favorite method. So we could use Monte Carlo. If we use Monte Carlo control, then that gives us a method called Monte Carlo search. If we apply Sasa, that gives us a method called TD search. I'll talk about both of those. This one's particularly well known. So pick our favorite model-free RL algorithm. It's not meant to be exhaustive. You could pick anything. You could use least squares policy iteration. You could use, you know, pick your favorite method, apply it to your simulated experience, and you have a search algorithm. So what does this look like? So let's start with the simplest possible version. This is what I call simple Monte Carlo search. So let's just assume that we've got some model, or someone tells us the rules of the game, or we've learned our model of how the rocks are working, or how the robot's walking, helicopters flying, and we have some simulation policy pi. So simulation policy, it's just some way that we are going to pick actions in our imagination. And now what we're going to do is we're going to consider, from our root state, we're going to consider all the actions we could take from that root state. So we just consider the root of this tree. So I could take action, I could go left or I could go right. I could move my hand here or I could move my hand here. And for each one, I'm going to generate big K episodes by sampling from our model and from the simulation policy. So we're going to pick actions according to our own simulation policy. We're going to see how the world transitions by using our model. And then we're just going to evaluate each of these actions in the simplest possible way by Monte Carlo evaluation, which just means we take the mean of the returns. In other words, you know, if I'm saying I could go left, and if I go left, I'm going to run 100 different simulations where I go left, and I'm going to see how well I did on those 100 simulations and take the mean of all the returns, and that's going to be my evaluation of how good it is to go left. Then I'm going to do the same thing for going right, run another 100 simulations, take the mean of all the returns for going right. That's going to be my evaluation of how good it is to go right. We evaluate each of those in turn, and what we see is that if we just evaluate our actions, that gives us an action value function for the root of this search tree, starting from my root, considering all of the actions I could take, and just taking the mean of these returns. That's all we're saying. And all this is saying is that this thing, by the law of large numbers, really does give us the true value function for our simulation policy. If we run enough simulations, we really will converge on the expected value of those returns, which is the definition of the value function. And then all we do is we pick actions, we pick the real action to take. Now, do I go left or do I go right in the real world? Well, I just pick the one which had the higher mean, the one which did better in my simulations. That's the idea of simple Monte Carlo search. Is that clear? That's the method? Yeah, question.
How is the simulation policy related? So, like, if your simulation policy is pretty poor, it wouldn't really work, right?
Yeah.
Do you update it as you go? Or?
That would be the next slide. So here we're talking about simple Monte Carlo search, which basically is the simulation policy is fixed. More sophisticated methods are going to improve the policy as we go. So yeah, great question. Okay, so now I'm going to tell you about something which is actually a state-of-the-art search method. This solves really challenging problems. It's a very effective planning method. And I'll give one brief case study from the game of Go, where this is the only method which has been able to achieve strong human-level performance. So let's assume we have some model. And now, again, what we're going to do is we're going to start from the root state. We're going to generate trajectories of experience starting from that root using a current simulation policy. And the difference is that now we're actually going to view this thing as something which is like living. This policy is going to start to improve over as we start to do this. And what we're going to do is, instead of just evaluating, you know, the root actions of going left and going right, we're going to evaluate every state action pair that we visit. So we're going to start to build a search tree that contains all of the states that we visited so far and all of the actions that we've tried from those states so far. We're going to build a search tree up. So we're going to basically have something where we're going to have something, you know, like one of these pictures where every step we're going to run some simulation out, and at the end of that simulation what we're going to do is we're going to store an action value basically for all of the actions that we can take from all of the states. We're going to store a Q value here, a Q value here, a Q value here, a Q value here. For everything that you revisit, we're going to start to estimate how good is it to be in that state and to take that action. We're going to start to estimate all of those Q values, whereas in simple Monte Carlo search we were just doing it at the root. And the way we're going to estimate those things is in the obvious way. We're going to do it again just by taking the mean of everything we've seen from that point onwards. So if we want to know, if we're in this state and we take this action, how good is it? What we're going to do is we're going to consider all of the simulations that have passed through this action, and we're going to take the mean of those returns. And that's going to be our estimate of how good it is to be in this state and take this action. So we basically just record in every part of our search tree, we record these Q values. And this thing is just, again, it's just counting. This is our fancy notation for saying let's just take the mean of all these returns and look at all the times we actually pass through that state action pair. And what do we do? Well, at the end of the search, what we're going to do, again, we're going to pick the action that has the highest Q value at the root. But there's one big difference now, which is we've got this rich information in our search tree, and we can use that rich information in the search tree to make our simulation policy better. So the way we do that now is that after every simulation, we're going to make our simulations improve. And we do that in the same way that we do policy improvement in previous classes, where we're going to basically look at the Q values, we're going to maximize over the Q values in the search tree to make them better. Now the only distinction is that here we don't have a complete table of Q values everywhere, we've only got them within the search tree. So we break up our simulation into two phases, whether we're in the tree or whether we've gone beyond the tree where we just don't have any information. So when we're in our tree, then we improve our policy. We pick actions so as to maximize the Q values that we've got stored in our tree. So every node of our tree, we just look at our children, I look at all the actions I can take, and I just pick the action which gives the highest Q value, possibly with some exploration as well. But when I run beyond my tree, and I don't have anything stored, I haven't seen these states before, I just behave according to some default random simulation policy, which again can be naive. But we're expanding the frontier of what we know about until eventually our simulation policy becomes smart everywhere. And so the algorithm is that every simulation, we evaluate our states by Monte Carlo evaluation, but then we improve our policy, our tree policy, by, for example, epsilon greedy, or smarter strategies using bandits. And so this algorithm, it turns out, is one we've already seen before. It's basically Monte Carlo control but applied to simulated episodes of experience that start from the root state. So we're always starting from the state we're in. We're starting from this moment now. We're running our experience from now onwards. We're applying Monte Carlo control to the experience that we encounter from now onwards. So it's our familiar methods from before, but applied to do search, applied to focus on what's going to happen next and understand this rich set of contingencies. And because it's Monte Carlo control, we already know that this thing works. And in fact, what this tells us is that this thing actually has to find the optimal search tree. It has to find the optimal solution, the best possible way to behave from this state and this action onwards. You know, this tells us how to find the best action from now onwards. If we keep running this forever, we continue to explore all state action pairs and do the usual things that we need for convergence. Okay, let's make this concrete with an example. So this is the game of Go. I used to work on this. It's a fun problem. It's the oldest game in the world, 2,500 years old roughly. And what's interesting about it is that it's considered to be like the hardest of the classic board games that people play. And it's considered a grand challenge task for AI. And back when chess was solved, you know, everyone shifted over to consider Go instead because it was considered a much more challenging, interesting problem for computers. It was considered a problem where you needed these kind of magical human intuitions to do well, because brute force search just didn't get anywhere in Go. So the traditional approaches to brute force search, which was so effective in chess, basically didn't work in Go. And So let's just very briefly understand the game. How many people here have heard of Go or played? How many people know the rules? Okay, about a quarter. So very briefly in one slide, you take a board, which is usually 19 by 19, but can be smaller. I'll illustrate it with some smaller ones. And the idea is you just, black and white, take turns to place down a stone at some intersection. And there's basically two rules. The first rule is that if you completely surround a stone, then it gets captured and removed from the board. Or if you surround any contiguous block of stones, similarly they get captured and removed from the board. And at the end of the game, the player with more territory wins the game. So this is an end game position, and we see that black has surrounded this number of intersections, but white has surrounded more intersections over here, so in this position white would have won the game. And so the goal of the game is to kind of place down your stones in the way that maximizes the amount of territory you get. Okay, so it's a fun game. Okay, so roughly what we're going to do, and we'll talk about this more in the games lecture, is we're going to consider a particular reward function to turn this into a reinforcement learning problem, to turn it into an MVP. And in a game, what we really care about is winning the game. So let's define that in our reward function. Let's say we're going to have a reward which is 0 for every step that's intermediate where we're still playing. It's like the chess example we talked about earlier. And then at the end of this, we'll talk about a reward that's 1 if black wins, and then 0 if white wins in the final terminal position. And then what we're going to do is we're going to consider policies for both sides. We're going to do this by self-play and consider, we're going to pick actions for both sides. We're basically going to now try and learn a value function, which essentially tells us how good is some position S. Like if I show you this board configuration, is it good? Is black going to win or is white going to win? I want to know if this thing's good. And we define it in the usual way, but because it's a two-player game, there's just a little twist. So now when we do our rollouts, when we do our Monte Carlo evaluation, we're trying to learn the expected value, like will I win on average from this position, the probability that black wins from this position. But what we really care about is the optimal value function, and this is why we need a search tree. And the search tree is trying to find something like the minimax value. Like if black is trying to, it's the best way to play if your opponent's trying their best to beat you, and so forth, all the way down the tree. We'll get more into that in the final lecture. So Monte Carlo evaluation looks something like this, where you might start in this. This is the simple Monte Carlo evaluation, no search tree yet. You start in this position here, and I want to know, well, am I going to win or not? And so what we can do is we can just roll out some games using our simulation policy. We're going to try 4 different versions where I'm going to imagine what happens next 4 different times without really playing my opponent. In each of those I might see I won 2 of them and lost 2 of them. And so now I can say, well, I've got an estimated value for this position, which is 2 out of 4 or 0.5. So it's a very simple way to estimate how good a position is. And it turns out that, actually using, complicated value function approximation, it's very hard to get a value function approximator using, sophisticated machine learning methods. It's hard to even do as well as this naive approach, because this thing is kind of dynamically probing how good the position is from now onwards. We're sort of really focusing on this start situation. We're ignoring all the many other games that we might be in that are just irrelevant to us right now. It's forward search. Okay, and now to turn this into a tree search algorithm, what we have is we can apply this Monte Carlo tree search idea now. And I'm just going to walk through a few iterations of this algorithm to make it concrete. And so what we have here, this notation basically tells us that we've got some state that we visited for the first time. So this is something we're adding into our search tree, so we'll mark that with a star. We add in this state. I'm going to say, okay, I'm going to start in this root state. I'm going to run some rollout. So these diamond states are things that we don't store in our search tree, but we just pass through until we end up in this square state, which basically means the terminal state where we finish the game. And the 1 means that we won that game, or the black won that game. Okay, so black won that game. That was the reward that we saw at the end. And so now we can start to fill in the values in our search tree. So we started here. We ran a simulation to the end. Black won. So we can start to source some statistics in this node here. We can say black won 1 game out of 1 from that node onwards. So let's run 1 iteration further. So now we start back at our root state here. This is the position I'm really in. I'm trying to figure out, this is now, and I'm trying to figure out what to do from now onwards. And I'm building up my search tree of all the things I've visited so far. And so now I'm going to add in a new position into my search tree. I'm going to run a new simulation from here onwards. This time, white ended up winning, so that's a value of 0. So now I can say, well, this new node, we got 0 out of 1 from there, and this root node has now had 1 out of 2. So we can start to get more sophisticated information at the root here. And now we can use this to start to guide our search. So we can say, okay, well, this wasn't so successful for white to, this wasn't so successful for black to get 0 out of 1 over here, so maybe black should choose a different move. So we use the tree policy to guide us. And so now black can choose this new move over here, add that into our search tree, run a simulation, see that black wins this time, fill in this with 1 win out of 1. Now we've got 2 out of 3 wins at the root. Continue. And as we start to continue this, we see we get richer and richer contingencies in our search tree. And we're starting to expand this tree of look-ahead possibilities towards the things which have been most promising. So now we see, let's go this way again. It worked for us before. This is looking better than this. So let's try going this way again. This time we added a new situation over here, a new state we haven't seen before. Run a simulation. White wins. Back that up. We've got 0 out of 1 here. 1 win out of 2 here, and now 2 out of 4 at the root. But this still looks better than this. So now we can run another simulation, and we start to expand the parts of the search tree which are looking most promising. So we run again, get a win for black, back this up all the way up this path here. And what happens is as you run this algorithm out, you see that it very deeply develops the parts of the search tree which are most promising, which are leading to the best results for both players. And it completely ignores the parts of the search tree which are useless because they're getting bad results. And what you need to do is just make sure that you continue to explore these bad parts of the tree a little bit to make sure that you don't ignore them completely. Yeah, question?
But you've run the policy just for one trajectory there, right? And there are many possible alternative trajectories from that point, which you may...
From this point onwards. Yeah. So we're making an assumption, we're making a simplification, which is that our simulation policy is acting as a reasonable proxy for doing a deeper search down here.
Canonical sort of trace for that point in the tree. But I mean, how realistic is that? I mean, there are many alternatives.
So there are many alternatives, and it might be that you miss some information here. But the good news is that over time, we're just going to develop the tree further and further and further. And so this thing is just acting as a heuristic to guide us towards the best parts of the space, and eventually it gets replaced by the real information in the tree. And so asymptotically, any bias that we introduce in this simulation policy gets removed as we go further and further in. And in practice, it does matter a lot which policy you choose here, but nevertheless, even with very naive policies, even if you just pick things uniform randomly, this strategy works very, very well. So uniform random isn't as dumb as you might think in many situations. Okay, so why is this a good idea? Well, it's highly selective. It's a kind of best first search, where every episode we kind of go back to the root and get to pick again which path we want to follow through this search tree. So every iteration we get to pick, actually this way is better than this way. So it's a kind of best first search. And it evaluates states dynamically. It's not like dynamic programming, which is focusing on the entire state space. Here we're dynamically evaluating the position we're in right now. We know that we're in this position, so let's invest more resource into that position dynamically rather than offline learning some function approximation that has to cover the entire state space. Using sampling, sample-based planning method, which breaks the curse of dimensionality. We don't have to consider all possible things that we might do or all possible things the environment might do. We just sample them and look at what's working well. And it works for black box models, so we only need to use our model to sample from. So this thing works well, it scales well, it's any time, you can parallelize it, it's got lots of good properties. So just to go back to the Go example, how does this work? So this is a plot of how strong Go programs have become over time. And what we see is that these asterisk programs down here were the state of the art before this Monte Carlo search algorithms came around. And then what happened is the first Monte Carlo search program, Mogo, and Crazy Stone, these guys came along and made these big leaps forward in performance that very quickly kind of overtook. And there's been this steady progress. All of these programs are Monte Carlo programs. And actually, if we continue it out to today, we're now playing at around 6 Dan, which is roughly as strong as the strongest players in the UK. for a problem that was considered to be something that humans would always dominate computers over. So until this algorithm came along, there was no alternative really. So it's very effective, particularly in large, complicated domains where where brute force search isn't effective, and you need to be selective and you need to dynamically evaluate positions because you have no real idea of who's winning or losing otherwise. Also works very well in MDP, single agent domains. It's a widely used tool across reinforcement learning now.
Can you explain the y-axis?
Oh, sorry, yeah. Yes, I should explain this diagram. So this is time. The y-axis is the strength of the Go program over time. This is the rankings that humans use. So starting from Q levels, which are like, so lower Q is better, and then higher down is better. So it's like kind of, one down, it's like getting to black belt or something and go, and then it just gets stronger and stronger up to about 9 down. That's what this axis, and it means, so the difference between one, so this distance difference here basically means that if this player gave one free move to this player, they'd be at an equal strength. So that's how you calibrate this scale at every level. Okay, so having advertised this Monte Carlo tree search approach, Monte Carlo search is a very effective method for planning, I now want to just bring us back and say that's just one example of a family of very effective search algorithms. And I really don't want to give the impression that you have to commit to this particular way of doing Monte Carlo with this particular tree structure and this particular simulation policies and so forth. It's the key ideas are doing forward search and sampling. If you use those two ideas, you can get very far. That brings you to really good parts of the state space and applying model-free reinforcement learning methods to those simulations. So what if we consider other model-free reinforcement learning approaches? So what if we do our simulation-based search idea? So we start from now, we imagine trajectories of experience, but instead of applying Monte Carlo learning, let's apply TD learning, let's apply SASA, let's apply our familiar bootstrapping-based methods that were so effective earlier in the course and which we saw were generally tended to outperform Monte Carlo learning. And so the main idea is to, where Monte Carlo tree search applies Monte Carlo control to the sub-MDP from now, we're going to develop something called TD search, which applies SASA to the sub-MDP from now, just to build that spectrum of ideas and show you that there are many possibilities. And so why should we do this? Well, because we've seen that bootstrapping is helpful. We've seen when we're doing model-free RL, when we're not planning, but in our usual setting of just reinforcement learning, we saw that TD learning reduced variance, it could be more efficient than Monte Carlo, and when we found this lambda parameter that we were often much more efficient by trading off between Monte Carlo and bootstrapping. And the same is true when we use these planning methods for simulation-based search. So TD search can reduce the variance and increase the bias. It's usually more efficient. There are some exceptions to that, but on the whole, it can work very well. And if you choose the lambda parameter well, you can do much better than Monte Carlo backups. So what does it look like? Well, what we're going to do is we're going to start again from our real state, our start state. This is now. This ST is now, our moment now. But now we're going to estimate a value function, an action value function. And we can do it in the same way. We can store this in the nodes of our search tree. But for each step of simulation, what we're going to do is, instead of waiting to the end of the episode and taking the return of that whole episode and estimating values by the mean return, we estimate it by temporal difference learning, by bootstrapping, by saying, the value of being in this node here is the reward which I got for one step, plus the value of the node I ended up in after that. We bootstrap. And this is particularly effective in domains where you can reach states in lots of different ways, where you're not just building a strict tree, but you can actually get back to states in lots of different paths, in which case bootstrapping is very effective because you might have seen your child from another path, and you might already know something about the value, and now you reach that same state again from some other path, you already know that it's a good state, not a bad state. You don't have to just run out new trajectories. So we update our action values by SASA, for example, and we select actions by acting greedily with respect to our Q values, just as before. So the only thing we've changed from Monte Carlo search is the way in which we update our action values. We use temporal difference learning instead of Monte Carlo learning. And that can really help things. And the only thing I want to point out, but I'm not going to have time to go into, is that you can also use function approximation here. There's no reason that you have to represent your Q values for either Monte Carlo search or TD search. There's no reason you have to represent your action value function using a search tree or using a table lookup. You can use a function approximator, and that can help a lot. So I can talk to you about that afterwards. We have some nice examples, like for the game of Civilization, a computer game, where that really helps a lot. You have to do that if you want to be effective there. State space is too big otherwise, the action space. Okay, so last slide, and then just one result slide. So let's come back to the diner idea. So what was the diner idea? The diner idea said, well, we don't just have to learn from real experience, we don't just have to learn from simulated experience, we can combine these things together. So let's do the same thing, but with our forward search algorithm now. So this is the idea of Diner 2. And the idea of Diner 2 is it basically maintains two value functions. You can think of these as like a long-term memory and a short-term memory, or a working memory. It basically updates its long-term memory from real experience. It's basically got one set of, one value function, one saying how good things are when you really experience them, which is kind of the general domain knowledge. And you also have some short-term memory. This is like your search tree now. Your search tree is the thing that tells you how good is it in my search tree. Starting from now, I'm going to learn from simulations and update my search tree and say, you know, in this search tree, I've tried a few things, I've done my TD backups, and I figured out in this particular situation I'm in, you know, it's a really bad idea to go and put my hand up here because I know that in this particular situation I'll fall off the rock. This thing tells me that, you know, in general, it's a good idea to move your hands like this. This thing tells me that I've done some look ahead from this point onwards, and I know that in this situation, this rock is loose, and I'll probably fall over if I move my hand here. So the idea is we maintain two different types of memory. We update one of them from real experience, and one of them from simulated experience. And then we combine them together to sum these two together to give us our overall value function. I'm sorry I don't have time to give more details. I'll just put up one plot, which is just the final slide on this kind of Go example, just to show what happens when you combine these ideas together. So this y-axis now is the winning rate against a standard benchmark program called Nugo. This x-axis is how much thinking time we do, like the number of simulations that we run before making an actual, thinking an actual move. This dashed black line is a Monte Carlo tree search, the effective method we looked at before. And now what we see is what happens if we use temporal difference learning instead of Monte Carlo learning. So if we were just to apply temporal difference learning to real experience, this is learning about the whole state space of Go and not specializing on the situation I'm in right now. So if I was to learn about the whole state space for Go, I get this very poor winning rate of around 5%. If I apply exactly the same updates, exactly the same SASA updates, exactly the same representation of Q, everything exactly the same, but I apply it to simulated experience, doing this forward search idea, it immediately it does much, much better. We get so we need to do a minimal amount of computation, maybe like 1,000 steps of computation, and then we start doing really, really well and outperforming Monte Carlo tree search because bootstrapping is effective. And finally, the Diner 2 idea is this blue line here, which combines the best of both worlds. This is something which learns about real experience by running real trajectories, and so this means that we're actually able to learn from real experience, and even before we do any thinking, we already know what to do because we've got this general knowledge about how to behave in general. And we also have the specific knowledge about the current situation we're in. We learn about the wobbly rock and exactly how to adapt to the current situation. Okay, that's it. I know there's a lot of ideas there. I really just want to emphasize the main ideas that planning and simulation-based search, an effective method for planning, is to use our model just to sample trajectories, to imagine what might happen next, and apply your favorite reinforcement learning method, whether it's Monte Carlo control, SASA, combining real experience with simulated experience in this Diner way. The main idea is that learning from simulation is an effective method for search. That's the final section of today's class. And this really works well in practice. Okay, next week we're going to talk about exploration and exploitation, and the final class we'll talk about the games case study. Thank you very much. Oh, one final thing, which is if people are interested, I should advertise that DeepMind are recruiting. So if that's something you might be interested in, then I will say, let me just flash up the right slide. So if you're interested in that, then you can wait 1 second and I'll flash up the correct slide with the right email address, and then you can contact that email address. Thank you very much, everyone.
Sorry?